recorded loop. Okay, so what I will do is mostly I will use the so-called MATLAB live script. So I have my standard version of MATLAB. I will tell you various things that are only my implementation has later on. But just to recall a few things that you should know when you work with MATLAB. So once you have started MATLAB, you have essentially basic structures, and the early versions only had matrices and strings. So you can say, well, matrices, what about vectors? Well, a vector can be a column vector or a row vector. That's just a degenerate matrix of size 1, either in terms of height or width. So how can you generate matrices? Very easily. First of all, you can generate a vector by arithmetic progression. So 1 dot semicolon 7 gives you the numbers from 1 to 7. So you see it to the left-hand side. If you're having arithmetic progression starting at some point, so that's the first point in the arithmetic progression with a step width, then you just give the step width, and as soon as you're passing the final argument, you're leaving it out. So maybe just to show you R2 as a column vector. So the comma means transpose conjugate, but since we are having a vector which is only, sorry, I have to move my bar a little bit away. Since I have only a vector which is real valued, it's of course the same. So I'm just changing it. So you see now it stops at 1.9 because the next number, if you progress with 0.3, would be 2.2, and that's larger than 2. So if it's included, it's coming up. Sometimes you want to arithmetic progressions, you don't want to compute the distance in order to get equidistance, and then the linear spacing command is quite useful. So if you need 5 points between 1 and 2, you get a linear spacing starting at 1, finishing at 2. So it's A, B, and number of points. So it's a vector of length 5. Standard matrices that you're creating are these ones. A matrix of some format, you can also put ones of 3.5 would be a matrix with all ones of format 3 times 5. As you know, height is the first argument. Very important is, of course, the unit matrix or identity operator. So of size 3 is a diagonal matrix containing constant 1 in the diagonal. The zero matrix is zeros of format, and an interesting thing is that MATLAB, whenever it gets a matrix, is viewing it as a collection of column vectors. So very soon we will see, or we can, we could maybe do a plot of this here. Yeah. If you plot a matrix, 2, 3, then it would say, well, get as information a collection of column vectors. And so it would say, well, maybe first of all, I tell you what's happening here. So T3 was from the beginning any matrix. So more or less you keep the shape and you fill in data. Now, if you fill in a vector which has 9 components, how would you fill it into the vector scheme? And the answer is in this way. You take the vector and first you fill in the first column vector, then you fill in the second column vector, and then you fill in the third column vector. So you're always going in this way. So for example, another example that I could do here is maybe maybe I first show you. If you're plotting these things, it's clear that you have 1, 2, 3, 4, 5, 6. So you have linear progressions. And this also shows you how the current version of MATLAB is choosing the colors. So it starts with blue, reddish, and so on. So different columns are plotted in different colors until you have run out of colors, and then you start again. So this is quite good to know. Just as a side remark, if you look at this picture, you see that the distance between the first column and the second column is the same as the distance between the second and the third column, which means that if you add to the red guy the difference between red and blue, you get the third column, which means that clearly the rank of this matrix must be just 2. So let's do this in MATLAB. What is the command here? Yeah, put new bar, then I don't have to run. The rank of the matrix T3 is, of course, by running the section, is of course somewhere hidden. My windows are a little bit. It's hidden somewhere. Yeah, here, the rank is 2. Now, the way to understand it, you could also, I mean, if you are doing it by hand, how would you compute the rank of a matrix? I guess you would apply Gauss elimination. So let's do row reduced echelon form, which is Gauss elimination applied to this matrix. And let's see what you get from this. And what you get here is, you see here 2 pivot elements, which means the first column is non-zero, so you get a 1. The second column is not dependent, so you get the second pivot element. And maybe that's a surprise to you, the third one is not just having a 0 and no pivot element, but it clearly has the information about how much of the first vector and the second vector you get. Remember, the second unit vector, if you take it and you add the difference between the second and the first, then you have 2 times the second and minus 1 times the first one. So you just have to remember what Gauss elimination is doing. Gauss elimination is allowing 3 steps. And each of them is an invertible matrix by an elementary matrix multiplied from the left. Now, the important thing is that you are always multiplying from the left and that you have invertible routines, so that by the fact that you're having something invertible, linear relationships between the things on which you operate by matrix multiplications, and these are the columns of the original matrix, they will be preserved. So if you have, after some invertible mapping, a linear relationship of 2 times the second guy minus 1 times the first one, then this relationship must have been available in the original matrix. On the other hand, if you multiply from the left, you're providing, you can also see it that you're doing it row-wise. So how do you matrix multiplication? You choose a row of the matrix that you apply, and you do some manipulations. So you are not changing the row space. So what can you learn from this? Just repetition from linear algebra. If you see this particular shape, I can tell you that the column space will be 2-dimensional, and the first and the second column of the original matrix, important. You're changing the geometry, but you're not changing the linear relationships. So the linear basis for this would be these 2 things. On the other hand, you can say you did not change the row space. So these 2 vectors, first and second row of this, are spanning the row space. And of course, this is the vehicle that you get in order to show that the dimension of the row space and the dimension of the column space are equal. But here we have even found a way to produce a basis. Okay, the point was more to remind you of linear algebra facts. How do you get complex valued random vectors? Well, you say, take a random vector and you see here, or you can test it, you get numbers uniformly distributed in the unit interval, so from 0 to 1. And the same for complex valued. Now, if you're interested, and maybe I'm doing this, in complex valued things which are not positive, so real and imaginary part should not be positive, because that's sometimes, then you're just subtracting from the real part and from the imaginary part 1/2. So the range will be -1/2 plus 1/2. And this is a private command, so this is not standard MATLAB. And the random CN means complex normalized. So yeah, I didn't assign it, but maybe that's a good moment to demonstrate here. The last unassigned vector or result of a computation is the output of this, and what is the norm of this vector in the Euclidean sense, and you get here it's 1. So this CN stands, I would like to have a balanced random vector of length 1, but with distribution of real and imaginary part independently and in some range, but the normalization gives you the actual range of these values. Now, as I mentioned in the beginning, the MATLAB does not allow or doesn't have a priori does not have a scalar product as a command, so you have to do a scalar product yourself. So if you have such a vector, then the Hermitian, that's why I call it XH, the Hermitian is the transpose conjugate of the vector. Now, I can compute, this was the random vector, I can compute the norm. That's of course the Euclidean norm, and as we know and expect, it's the square root of the scalar product of x with x. Now, the only thing I want to mention here is the scalar product of two column vectors x and y has been written as y prime with x. This is due to the tradition in mathematics that you would like to have the y, the second component of the scalar product, to be conjugate. So what does it mean here? If I do this x prime with x, then you get the first component of x, x1 conjugate. So you can think of y1 conjugate multiplied with x1 plus y2 conjugate multiplied with x2. And that's of course exactly the scalar product. This is not the main reason, but one of the reasons why most of the time I prefer to work with row vectors. But by transposition, of course, everybody knows how to replace left matrix multiplication on column vectors by right matrix multiplication on row vectors. So what happens if you are taking maybe I'm coming to this a little bit later. So first, I'm doing another example of a matrix. Here it's a real valued random matrix 4 by 4, but I replace, and that's showing you essentially how to work with individual columns. I replace the column number 3. So a complete column is anything in the first component. That's the usual meaning of this double dot, but it's a different use of compared to above. And then number 3, so the third column gets new assigned. So the left-hand side is the new value, and it's obtained by 2 times the column number 1. So this is this original matrix minus 1 times, or I could make it, I don't know, let's make it 3 times the second column. Now, if I do this, I kind of repeat the random number generator, I get a new matrix, and then I apply the row reduced echelon form. So I didn't show it to you. And we see and we know, of course, how it was created, and you see that these numbers are telling you. So once more, going back to the story about Gauss elimination, the result of the non-pivot columns are showing you how they can be linear, obtained as linear combinations of the earlier columns, and you get the correct linear relationships. Okay, so I was mentioning already how to get the columns, a basis for the column space, but it will be interesting to know how to project on a subspace. So you can imagine, I don't have, yeah, maybe, if you, yeah, okay. You can imagine how to do it. So in order to do this, I'm going in this case, this is now a four-dimensional case. I'm saying we have seen, yeah, partially you have seen the third column is of course 0, 0, 1, 0. So that the third column is linear independent and the rank of this particular matrix, because it's a random matrix, is expected to be 3. So we can do Gram-Schmidt, and you can also apply the ORT command. That would be a different thing. Maybe I'm doing this. OB is ORT B, and again here I'm saying I'm taking all the columns which have the numbers related to the index sequence 1, 2, and 4. So I'm just eliminating the thing. And now I'm asking, are these things equal? I'm actually not sure. I don't think so, but that's a small experiment. Okay. Yeah, okay, so that's too spontaneous. Maybe I'll leave it out here. I just put it as a comment to be done later. So the Gram.
Yes, there's just one column missing at the end, and it would work.
Oh, thank you. Yeah,
Yes.
Thank you for being so observant.
Not column parentheses, yes.
yeah, of course, yeah. I see. Of course, I have to compute the norm of the difference. I'm not. Yeah. Okay. Well, this looks as if you would get the right. It is speculation now. Okay, now. So probably it would be interesting now to compare it. I mean, Orton. But I can tell you what the built-in command ORT is. It's just given a collection of vectors, it provides you with an orthonormal basis for the same space. And what you can do is, of course, as you're following the linear algebra course, you can do Gram-Schmidt. Now, I'm not sure, probably Gram-Schmidt is also somewhere in MATLAB, but I have my own version which kind of explains very nicely how to work with the projections. So I will leave this now and share the code with you, but it's not the point at the moment here. Now, the point is, Gram-Schmidt is clearly a way to generate a basis, an orthonormal basis for the three-dimensional column space of this 4x4 matrix. So how do you get the projection operator? So we all know if you have some three-dimensional subspace of R4, I'm doing it real value. No, it's real valued here, everything. Then I can describe the projection, and the answer is what I have to do, I have to first take scalar products. And now think of the matrix acting on a column vector, and you see that if you're having a collection of vectors, of column vectors, and then you make the transpose conjugate, you get exactly the rows with the conjugation which produce the scalar products. So this will be coming up very often, and you will get used to it. But so if you do a projection on an orthonormal basis, you know the coefficients are just the scalar products. So what is this statement? It's just saying, well, if you give me an orthonormal basis, first I create from a given vector the set of all the scalar products with respect to my three-dimensional orthonormal basis for the subspace. And then, of course, I'm doing matrix multiplication, which is synthesis. I'm doing exactly, I'm taking as much of each of those vectors from the orthonormal system as the coefficients tells me. And so I want to check, first of all, is this really a projection operator? Now, a projection operator, you should recall from linear algebra, is just an idempotent, which is self-adjoint. So if I look at this, what is the adjoint matrix to such a matrix? Well, you're moving GRB prime to GRB double prime, but twice conjugation and twice transposition is of course the original matrix, and this, the first guy is going this, so it's clearly, evidently by construction, at least numerically self-adjoint. But if I want to see that this, whether it's idempotent, I have to do this. Now, I could do the, okay, sorry, that's, maybe I just do the standard norm. So the norm is really the operator norm of this, where is it? Yeah, the first, no, and I didn't display, that's why it's gone. And the second thing is that I wanted to tell you that there is some command called the pseudo-inverse, which is actually the solution to the minimal norm least square problem of a linear problem, but this will be discussed at great detail later on. But what I want to show you is, maybe I'm doing it also in this standard way, I can show you that there are two ways of creating the projection matrix on a subspace. And the first one is determine a basis by throwing away the linear dependent elements and then doing orthogonalization, whatever you choose. And the other way is to combine the matrix with the pseudo-inverse. So here, if you would get a vector, you would say, well, I have to apply the pseudo-inverse and then I apply the matrix of the matrix. But what the pseudo-inverse is and all these things you will see later. So let's just do it once more. The rank of this system is, of course, 3. This difference is numerical precision, but also the next one is the pseudo-inverse. Okay, again, this should be done, should be made visible. So the pseudo-inverse computes combined with the B is the same as this orthogonal projection matrix. Okay, here you see I have done just a different way of orthogonalization as we saw before. And you can describe the orthogonal projection with this different, not the Gram-Schmidt one, but the arrow is the same. Now here you see I'm using my private command. Compnorm is compare the normalized versions. Very often you have two vectors which are equal in shape, but not correctly normalized. And then the compnorm would give me this here. Yeah, maybe just to demonstrate the compnorm routine, if I would say compnorm of T3 and 1 to 9, you remember T3 was my test matrix. Then this command would tell you, well, if you reshape everything to a vector in the natural norm, they're equal form. And if I would take, I don't know, 2 times this, and I run it once more, then they will say, oh yes, these two vectors are, you can compare row vectors with column vectors or so, and everything is fine. And just because this happened to me, I'm making a small experiment, 1 to 3. Okay, and now I would like to show you something funny. What is the norm? Yeah, comp norm of R3 or R. What was the name? R. Yeah. R and R transpose. And you expect, of course, that this should be, okay, maybe I did, yeah, I did not create the vector correctly before. So it's 1 to 3, a row vector with the entries 1 to 3. And of course, there's no difference if you are considering in this form. However, if you take the norm of R minus R prime, then you're getting something strange, which was, I just did some other thing and I was very confused or so, because normally you cannot take a difference between two matrices or vectors of different shape. But if you want to see it, you can show what happens is minus r prime is now actually something where you say, well, you're subtracting a matrix which is constant in one direction, and clearly this is not they're not equal or so. So that is a strange way of creating such a vector. Now, if you do the scalar product of a vector by itself, you're getting clearly just a scalar product. So this is 14. But if you're doing in the opposite order, so you're doing my row vector 1, 2, 3 multiplied with a column vector, then you're getting actually a multiplication table. So you're having 1 times the first column, 2 times this column vector, 3 times this column vector. So here you can read 1, 2, 3 times what you have in the first column, which was 1, 2, 3. So, and this is actually, if you take a normalized vector, this is the matrix on the projection operator. So this is quite good to know. Maybe I should stop doing pure MATLAB stuff, but some very easy final remark. So for random matrices, this is a random complex normalized matrix. It's not normalized in the sense of the ordinary norm. So maybe I should give you the norm command of this matrix. And then you see the norm is some number. The norm in the sense of Frobenius is 1, and the norm of the vector, which consists of 49 components, is also 1. Okay, so what is the norm? The norm here, MATLAB says, well, we store this collection of column vectors because it's describing a linear mapping. What is the norm of a linear mapping? That's the operator norm. So if you would have a diagonalizable matrix, you would say that's the absolute value of the biggest eigenvalue, or sorry, the biggest absolute value of eigenvectors. Otherwise, you would use the singular value decomposition. And that's why for big matrices, computing the norm is really more comprehensive. The Frobenius norm is just the Hilbert-Schmidt norm, if you're familiar with the concept of Hilbert-Schmidt norms, but it's just, for me, the norm of a matrix viewed as a pixel image. So you take the sum over all the squares of all the entries in your matrix. So you have a vector, here you make it explicit. You take a vector of length 49 and you take the Euclidean length. And so this is usually faster. And if you just want to know, are two matrices equal up to numerical precision, it might be easier to either move them into vectors or to call it Frobenius norm. Actually, the output of these two routines is exactly the same. So that's how it is done. Now, if you want to create a diagonal matrix, and this was a very simple thing with some entries, then I wanted to just demonstrate that, of course, the norm in the sense of the operator norm of a diagonal matrix, and the diagonal matrix is a multiplication operator. You do pointwise multiplication of your vectors with the entries in your diagonal matrix. And the operator norm, so this is the operator norm of a diagonal matrix with a random entries, and the maximum of the absolute values in your diagonal are, of course, the same. That's just a simple thing. And because here we have the command diag, it's nice to show that if you take our test matrix again, let's have a fixed command for this, and then you would see that the diag of the diagonal is, okay, the inner argument is take out the diagonal, which is the vector 1, 5, 9, and then you create in the second step from a vector a diagonal matrix with exactly these things. So for example, if you want to demonstrate the matrix is diagonal dominant, then you compare the original matrix with the diagonal matrix. And if this is smaller than 1, you're happy, because then you're saying most of the actions happens in the diagonal, and so everything is fine. Another thing that I find quite nice is you can look at this, because we have already seen the plot of the test matrix. So what is the rank of the test matrix of size, I don't know, 5? And then of course you will see it will be always 2. Now I have to show it, because the difference between the subsequent columns, even if it's a large matrix, are always the same, and therefore you can create it from the first 2 columns, and the row space is the same. Okay, I think I will stop now this part about pure MATLAB and matrix analysis with a little bit of linear algebra, and give this floor for